Hello, I'm Rajesh Shrestha, a first year PhD student at Oregon State University. Welcome to the presentation on our paper titled Exploratory Training When Trainers Learn. When we are training models to learn a concept, which can be a rule, functional dependency, or any kind of supervised to semi-supervised models, they are all dependent on human leveling. The applications like anomaly detection, sentiment analysis, and so on require accurate levels from human to learn accurate models. However, we humans aren't perfect, even at leveling things. We might not know the concept we are trying to model or might not be familiarized well enough with data. All these reasons may lead to inaccurate levels from humans. When humans are leveling the data, they themselves are learning, especially when dealing with huge data or when the concept we are trying to model is complicated. Let's look at an example. Suppose we have a financial data set with name, age, education, job, salary, and current balance of various people as shown in the table. We want to train a model to detect anomaly in this. As usual, a sample of data from the whole dataset is served to the human in an iterative fashion for the labeling purpose, where they would have to mark the rows that they think are anomaly. The first set of sample is served to the human. At looking at this first sample of data, the human's attention might be drawn to the first row with negative 10K balance. They might think that it's strange to have a negative balance and might mark it as an anomaly. Besides this, they might decide every other rows to be normal and move forward for the next iteration. Then another set of samples from the total data are served to the human for labeling. On observing the second sample, their attention is again drawn to the similar negative samples, minus 8K and minus 2K. They might recollect seeing similar negative data before. They might remember that earlier person with negative balance also had low salary. These people also have low salary like the one in the first sample. So it makes sense for these people with low income to have negative balance, that is debt. These rows now look plausible for the human. Upon seeing multiple samples of data, their previous belief about the data and model has changed. Human considers both these tuples to be okay. This example illustrates that over the course of labeling interaction, humans' belief changes, and upon seeing sufficient data samples, they find patterns in the data and learn about the data itself along with the concept we are trying to model. As we illustrated in the previous example, humans often do change their belief and their labeling behavior over the course of interaction. They might provide significant amount of wrong labels at the beginning, but might explore and learn as they are exposed to more and more data. Most current approaches for using the human labels for model training have certain implicit assumptions baked into them. They generally assume humans know correct labels from the very start of the labeling and has only a fixed small chance of making mistake. In addition, they assume that humans don't change their belief during labeling and don't learn during the process. These assumptions don't hold most of the time. These current approaches that considers almost all labels to be correct from the very beginning may fail in learning the accurate model. Now the question is, what can be done? How can we incorporate and account for human learning? One of the intuitive approaches could be waiting for humans to form their final hypothesis during labeling. Then we can use the labels provided by humans after they have reached their final belief. However, there are two major downsides to this approach. First of all, we won't know how long to wait. If the wait is too short, then the labels obtained could be inaccurate, while waiting for a long time isn't feasible either. This will lead to waste of important labels and time. This approach is also sample inefficient. Most of the labels from human during learning could be correct, but we are throwing away all those labels before they reach their final belief. Then what might be the better approach? Well, our vision is to build a system aimed to understand and adapt to the human learning during the labeling. It consists of two agents. One is the labeler, that is human who labels, and other is the system learner, that is trying to learn the concepts using labels from human. Both labeler and learner has some prior belief on the model we are trying to learn, and the purpose is to reach an agreement between them. The learner picks some examples from the data and asks for label. Based on this received data, the labeler updates its model and labels them accordingly. And based on the obtained label data, the learner also updates its model. Their models are changing over time, and the aim is to reach a common similar belief. Our approach has mainly two components. First one is human learning model that tries to replicate the human learning during the interaction. Models that are accepted in cognitive psychology and economics can be used for this. Another one is a system that adapts to human learning and solves data in a fashion to aid human learning. In this paper, we are focused on modeling human learning, and the adaptive system is a work in progress right now. Now, let's talk about the human learning models that we have used in our work. First human learning model is the Bayesian model. Research from cognitive psychology shows that humans learn using Bayesian update. Let's look at an example. Suppose we found a coin and want to know what's the probability of getting hit for that coin. Based on all the coins we have seen in our life, it's common to assume that this coin is also fair. That is 0.5 probability of getting head and 0.5 for tail. Hence in the graph we can see that our belief is centered around 0.5 value. Then we observe some samples that is affected by the probability of getting head of the coin. Let's say out of 14 tosses, we obtain 2 heads and 12 tails. Based on these observations, the coin doesn't seem to be fair and appears to have probability of getting head much less than 0.5. By the combination of our prior knowledge and the strength of the evidence observed, we update our belief, which has a peak at value less than 0.5. In our case, the belief on the probability of getting an head generalizes to the model we want to learn, and the data sample generalizes to the label data we get from human that is representative of the model that we want to learn. Another model that can be used for modeling human learning is hypothesis testing. This is similar to the one in statistics, but has some differences. Under this method, we choose a model that is more plausible based on the observed information. Let's look at the same example, where we want to find whether probability of getting head is 0.5 or not. Then we compute how likely is this model based on the observation we got. If we compute that H is very less probable based on our observation, we set a threshold so that if the probability is less than that threshold value, the model is discarded. If that threshold value is 0.05, then we reject our model of probability of getting head being 0.5 as it has value lower than the threshold. We performed a user study which was focused on learning functional dependency. It had 17 participants and there were 5 scenarios within it. Each of these scenarios had different attributes with different difficulty levels and based on different data sets. The users had to specify their hypothesis and mark the cells that they think are violations within the sample. For more information on the user study, you can refer to our paper. Now, let's talk about our findings. Here, the x-axis shows the iteration of interaction and y-axis represents the F1 score of human labeling on each iteration. Higher the value, more better it is. We can see that the value is low at the beginning and there is increasing trend representing human learning and getting better as they see more data. This is for scenario 2. More or less similar patterns can be found in other remaining scenarios too. All these plots show that humans are learning and getting better over time. Here we look at the average change in F1 score between iterations. We find positive change for every scenario which confirms human learning during the process. The users are refining their hypotheses as they absorb more and more data. The change in user behavior is not due to user error or noise, but is actually because of user learning. We did perform some statistical tests to confirm that. Now, let's look at how human learning models perform. This bar graph is showing how well do models replicate the human learning. Here, Bayes represents the Bayesian model and SP represents hypothesis testing model. This consists of mean reciprocal ratio MRR value for top 5 output of each model. MRR is a ranking metric. The higher the rank of users' hypothesis in the model's output, the higher the value of MRR. Hence, higher value is better. If we look at the performance, Bayesian model performs better than hypothesis testing model for all scenarios except scenario 2. Bayesian model replicates the human learning better compared to the hypothesis testing model. So humans may learn during labeling, and a better way to adapt to that is modeling human learning. Bayesian model better replicates human learning in most of the cases. This is an initial part of our ongoing work, which is improving our human learning model and developing an interactive intelligence system. This system will exploit the human learning model and presents the data to assist human learn faster and as a result reduce the interactions required. Thank you.